In the last video, we looked at optimization problems. In this video, we're going to learn a very helpful technique to solve optimization problems, which is called using the Lagrange multipliers. And we are going to introduce something called the Lagrange function, which will enable us to solve all sorts of optimization problems. Why do we want to solve optimization problems? Well, typically there are experiences or things going on, circumstances where there is something on the outside, some external circumstance that needs to be met. For example, a city wanting to build a public transportation system, and it only has a limited number of tax dollars that it can spend on the project. So given the number of tax dollars that it can spend, we want to figure out what's the best way to have a transportation system. So what we want to do is optimize some value under certain constraints. So let's think about, a very straightforward problem. Let's say that we wanted to maximize the production under a budget constraint, and that the production of F is a function of two variables, x and y, which are quantities of two raw materials. So our production equals x to the 2/3, y to the 1/3. Now let's imagine that x and y are purchased at prices of P1 and P2, thousands of dollars per unit. What's the maximum production of F that can be attained with a budget of C, $1,000? So what we're trying to optimize here is F. This is what we're producing. So we want to make F as big as possible. However, we're under the constraints that, for every unit of X that we buy, we have to pay P1, plus for every unit of Y that we buy, we have to pay P2, and this is our cost. So we know that this value here must be less than or equal to our budget of C, $1,000. And we have this written right there. So let's imagine a situation where the price for the first raw material and the price for the second material is 1, and that our budget is $3,780,000. So we get this following constraint, and this is our constraint. So given this constraint, what we want to do is maximize my function, or optimize it. Well, let's think about what's going on here. Well, given our function, what we could do is consider a bunch of level curves. And we understand what level curves are. Level curves are when we say, let's fix our dependent variable when f equals 1. And then we could solve this function in terms of y. So maybe we cube both sides, and we get 1 equals x squared y, or y equals 1 over x squared. And to simplify this, or to generalize this would be c cubed. And so for any value of z that we want to choose to look at, in this case 1, we're going to have a rational function, and here we have a bunch of our level curves. So for example, this is everything on this level curve has a value of production of 1. Everything on this curve has a production of 2. Here a production of 3. And then we're going to add our budget constraint. Well, our budget constraint is this linear equation. And we notice, by graphing our budget constraint against a bunch of level curves, so we have our constraint plus a number of level curves, what we notice is that anywhere on this constraint here, as we go in this direction, we're going from a production of 2 here, and now we're losing production. We're producing less. Similarly, after this point, we're producing less. So our maximum production occurs at that place where my constraint is what to my level curve? Well, it's occurring where my constraint is perpendicular, or sorry, is tangent to. So where constraint is tangent to my level curve, I'm going to maximize my production. So this introduces the idea of a Lagrange multiplier. So what we're saying is that where f is tangent to g, where g is our constraint. So where f is tangent to g, we will have our max or min value. Therefore, if we were to take the gradient of f and the gradient of g, since they are a maximum value when they are tangent to each other, well, when they're tangent to each other, we know that tangent is the same thing as parallel. So when f is parallel to g, or in other words, when their gradients are just different by a scalar multiple, so when my gradient of f equals some scalar, we call that scalar lambda, times grad g, we're going to have our max min. And this scalar is so important to us that we call this scalar, and this work was done by mathematician Lagrange. So this is the Lagrange multiplier. Okay, so how does this work? What we do is we, given some function, f of x, y, and we have some other function, g of x, y, which equals x plus y minus 3.78. We could find their respective gradients. So we have grad f equals 2/3 x to the negative 1/3 times y to the 1/3 I minus x to the 2/3 times 1/3 y to the minus 2/3 j. And this is my grad f. My grad g is simply I plus j. So what we know is that this system will be maximized when 2/3 x to the negative 1/3 y to the 1/3 equals lambda 1. So this is the I component of grad f plus lambda times the I component of g. And this should have been a plus here. So, and we know that x to the 2/3 with a 1/3 in front, y to the negative 2/3 equals lambda 1. So this is the j component, and this is the j component of grad g. So if we set these equal to each other, since they're both equal to lambda, we get 2/3. So writing this all in, so at this point it becomes just an algebra problem. So we can skip a step or two and generate the idea that this leads to the equation 2y equals x. And since we know that 2y equals x, we can go to our constraint and rewrite this as 2y plus y must be 3.78. And even though it's an inequality, I'm going to set it equal to it because we're going to maximize my production when we're spending as much as possible. Remember, this problem going back had to do with us spending money. So the more that we spend, clearly the more we're going to produce. So we'll make our constraint as big as possible. Solving this, we get y equals 1.26. And therefore, putting that back into our equation, we get x equals 2.52. So we found that x and y values, the number of each of those products that we need to produce to maximize our profit, or maximize our production, which is what we're trying to do. So then we could plug these x and y values back into my original function. And this shows us how much of each material we should use to maximize our production with a budget of $3.78 thousand, and that how much of our product we're creating is approximately 2 units. So let's try to summarize this a little bit. If we want to optimize some function, so our objective function, subject to some constraint, what we do is we look for the extrema among the points which satisfy the constraint. And we have the following understanding, that f will have a local maximum at some point, provided that that point is the biggest point for all points near PO, P naught. So our local maximum says that in that general area, that is the biggest value. And it's going to have a global maximum when that point is bigger than all other points satisfying the constraint. So this is the difference between local and global maximums. Local means that the point is the biggest point in the near area, whereas the global max says it's the biggest point of all points satisfying the constraint. And once again, graphically, what we see is that if we have our function here, our objective function, sorry, let me restate that. This circle is our constraint, because our constraint is fixed. So here's our constraint. And then we have our objective function at various levels. So various different level curves, f equals 4, 3, 2, and 1. And what we see is that our global max and our global min occur at the points when my objective function is tangent to my constraint. So here, when f equals 3, we've got a tangent line to my constraint, and same down here when f equals 1, which is my local minimum. So let's say that we want to optimize f given some constraint. Our methods for doing that says, well, if there's a smooth function f which has a maximum or minimum subject to some constraint, then that's going to occur at the point when my gradient of f equals lambda times gradient g. In order to find what that point is, that our maximum or minimum point, what we need to do is compare values of f at these points to decide whether or not it's a local max or min. And lambda we call the Lagrange multiplier. So we'll look at some examples in a little bit. So here we have a function which equals x plus y, and it's subject to the constraint. Our constraint is such that x squared plus y squared must equal 4. Well, it must be less than or equal to 4. Actually, it's on the circle, so x squared plus y squared must equal 4. So in order to find this, we find grad f, which is I plus j, and grad g, which is 2xi plus 2yj. So then the question is, we need to find when does I equal lambda 2x, and this is not I but 1, and 1 equals lambda 2y. This is all coming from the idea that grad f must equal lambda grad g. So their I and j components must be equal. So if we simplify this, we get 1 over 2x must equal 1 over 2y, or in other words, y must equal x. Well, given this, we could further simplify this to get that x squared plus x squared must equal 4. So 2x squared equals 4, x squared equals 2, so x must equal plus or minus square root of 2. So our points are going to be root 2 comma root 2 and negative root 2 comma negative root 2. And clearly, since our function is x plus y, without much work, we can understand that this value is going to be our max because it's positive, and this value is going to be our min. So we can graph that over here. Here's our constraint. Our constraint being x squared plus y squared equals 4. And then we draw a bunch of level curves for the function we're trying to optimize. So x plus y for a number of different values of f. And we notice that where f and g are tangent occur at the local max and at the local min. So just to be totally clear, in the last problem we were looking at optimization with an inequality constraint, going back to that production problem where we were looking at g of xy having to be less than or equal to c. So in truth, what we really should have done, so it's some function like that. What this function is really, what this optimization problem is really saying is that, x had to be greater than or equal to 0, and y had to be greater than, well, not greater than or equal to, but greater than 0, because x and y were how much of each product I was using. So we need to use more than 0 to create something. And then we had our cost line, which was that P1x plus P2y needed to be less than or equal to C, so we had this line here. And um, in truth, a maximum or minimum can happen anywhere in the interior. But what we recognized in that problem, and here's where sometimes you need to use your judgment, is that our maximum or minimum is going to occur on this red line, because on this red line is where I'm spending as much money as possible. So we know that we're going to produce as much as possible when we're spending as much as possible. And that's just common sense. So the general strategy then for optimizing some function given to some inequality constraints is to first find all points on the interior where the gradient function is 0 or undefined. So that was our first, this is what we looked at a couple days ago or a couple videos ago, that where our gradient function is 0 or undefined, we know we're going to have a local max or min. Once you examine the interior, then you're going to look at the lagrange multipliers to find the local extrema on the boundaries. Then you'll evaluate f at the points found in both the previous two steps and see which one is the biggest and which one is the smallest. So let's look at that. Let's find the maximum minimum values given this function subject to the following constraint. So let's first do our interior. So to find out our interior local max or mins, we're going to find out our gradient function. So gradient f equals 2 x minus 1 I plus 2 y minus 2 j. And by inspection, we can quickly see that this equals 0 when, or not when, at the point 1 comma 2. So is this a local max or min? We're not sure, but this is one of our points. Then we're going to look at the exterior. So a local max or min on the exterior is going to occur when grad f equals lambda grad g, where grad g equals 2xi plus 2yj. So we get the equation 2x minus 2, just expanding this, must equal lambda 2x and 2y minus 4 must equal lambda 2y. Well, if we do a little bit of solving here and solve for lambda, on the left-hand side, when we solve the left-hand side for lambda, we get 2x minus 2 over 2x. That's dividing by 2x. And on the right-hand side, if we solve for lambda, we get 2y minus 4 over 2y. Okay, well, let's simplify this even further. We can get rid of all the 2's. And if we multiply across, we're going to get y times x minus 1 equals x times y minus 2. simplifying this, yx minus y equals yx minus 2x, and this will simplify to y equals 2x. Well, since we have y equals 2x, we can substitute that into our original function. So we have x squared plus 2x squared equals 45. And if we solve that, we get x equals plus or minus 3. Now that we know what x is, and we know this expression between x and y, we know that we have two additional points, the point 3, 6, and negative 3, negative 6. So we have 3 points. These 2 points, which lie on the exterior, and the point that we found here, which lie on the interior. And so the last thing to do is just to evaluate our function for each of those points, our function being the one given up here. So let's write this on another page. We have our function, which equaled x minus 1 squared plus y minus 2 squared, and that was given. And then the points that we know are 1, 2, 3, 6, and negative 3, 6. So at these given points, if I were to plug 1, 2 into my function, I get 0. If I were to plug 3, 6 in, I get 2 squared plus 4 squared. And if I were to plug the negatives in, so clearly by plugging the point that makes our interior have a gradient that equals 0, and then the points where my gradient function, where the gradient of my function is parallel to my my constraints, I was able to find the possible 3 points where there was a max or a min. And then when I plug those points into my function itself, I find that this is where I'm going to have a minimum, and this is where I'm going to have a maximum. And this point probably is a local maximum, but isn't a global, because this is the biggest value. Well, what exactly does lambda mean? We've been introducing this lambda, but we usually solve it away and don't look at it. But what if we looked at lambda? So in this problem that we've been dealing with our production that we're trying to optimize and some constraint, when we first looked at the problem where x plus y equals 3.78, we found a lambda value. Well, we were able to find x and y, and if we were to plug those x and y values back in, we would be able to find out an actual value for lambda, which is roughly 0.53. Well, what exactly does this lambda mean? To inspect this, let's imagine that we, instead of spending $3.78,000, we spent $4.78,000. So we're going to increase C by 1. So the change in C equals 1. And going through this whole problem, we don't need to redo this exact same problem, but the corresponding solution would get you that x equals 3.19, y equals 1.59, following the same process, and our function amount would be roughly 2.53. 2.53. Before my production was 2. Lambda is 0.53. So my production was 2. It went to 2.53. My lambda value is 0.53. Huh. So my change in my function was from 2 to 2.53, 0.53. Well, while this isn't a proof, this is just showing the pattern, which is that the change in my function that I'm trying to optimize over the change in my constraint equals lambda. In other words, the value of lambda represents the rate of change of the optimum value f as the budget increases. So lambda is not just a meaningless term. It tells us a lot of information about how we can change our function, provided that we change our constraint. So let's think about using that understanding of lambda. It says the quantity of goods produced according to some function here is maximized subject to the budget constraint. So this is the problem we've been looking at. The budget is increased to allow for a small increase in production. So we're going to increase our budget. C is going to go up so that P goes up. What is the price of the product if the sale of the additional goods covers the increase? Well, interpreting our lambda as we understand it, lambda, which is 0.53, tells us that a change in my budget will result in a 0.53 increase in the change in production. So we can interpret that as if you increase the budget by $1,000, it will increase the production by 0.53 units. Because remember, just to be clear, that our budget, our C value is in terms of thousands. So let's write that a change in F of 0.53 when there's a change in C of 1,000. That's what this slope there means. Therefore, in order to increase the budget and make the increase profitable, we must make sure that we are getting enough money back. So in other words, let's say that we're selling our good for P dollars. So if we're selling each unit for P dollars, then if we increase how much we're spending, 0.53 P, which is our increase in production, 0.53 P is the revenue from the extra 0.53 units sold. So therefore, for every $1,000, 0.53, which is the amount of additional production, times the price that we get from each product. This value must be greater than the $1,000. So for every $1,000 increase, this must be, we must have 0.53p be greater than that $1,000. Let's say this again. We spend $1,000, we get 0.53 more production. 0.53p is how much money we're getting from that additional production. That's our revenue. And our revenue must be greater than the amount of money that we spend. Therefore, the price that we sell something must be greater than 1,000 over 0.53, which is $1,890. Summarizing this problem, what we looked at is the effect of lambda. And we said that our lambda of 0.53 meant that we'd have a change in production of 0.53 when we increased the cost by $1,000. And by what I mean by increase the cost, I mean increased our budget by $1,000. So we're spending $1,000 more. This is how much more production we get. The question was, how much would we need, what must our price be so that this increase in our budget was paid for by the price of the product being sold? So if we're spending $1,000 more and we're getting this much more product, then 0.53 times the price of the product must be greater than the amount that we spend, and therefore we'll break even or profit more. So this is our minimum selling price, so that as we increase the budget, the increased production pays for that budget increase. Interesting economics. All right, well, let's tie this all together and finish this up, summarizing this with the Lagrangian function. So the Lagrangian function, which is a function depending on x, y, and then the Lagrange multiplier, is defined to be our function that we're trying to optimize minus lambda times our constraint function. And before we get into it, let's just make sure that we understand some things. The gradient function of f of xy equals fxi plus fyj. And the gradient of lambda gxy equals lambda g partial xi plus lambda g partial yj. Okay, so we know this. And we knew from before we get into this down here, we knew before that when these equaled each other, so when fx equaled lambda gx and fy equals lambda gy, that we're going to optimize. Now, the whole idea of the Lagrangian function is it takes our two functions, the function we're optimizing and our constraint function, and it just puts them together in terms of a difference. So if we think about the partial derivative of our Lagrangian function with respect to x, that's just partial f with respect to x, which is this right here, minus lambda partial g with respect to x, and that's this right here. And when this equals 0, is the same thing as saying that they equal each other. And the partial derivative of L with respect to y is partial f with respect to y, which is this, minus lambda partial g with respect to y, which is that. And when that equals 0 is the same thing as saying that these equal each other. And then the very last statement, the partial of L with respect to lambda well, when we take the derivative of this function with respect to lambda, what we get back is just negative g of xy minus c. And when we set that equal to 0, all that's saying is that g x y, that gxy must equal c. So this is just saying that our budget, or rather our constraint, is held. And these two are forcing that the gradient of f equals lambda gradient of g. Or in other words, that our gradient, our optimization function and my constraint function are in fact parallel to each other, which we know will create a maximum or a minimum. So when all three of these are true, equaling to 0, our constraint is held and we're creating a tangent line, then we will be able to find out the point that maximizes or minimizes our optimization function. Let's look at that in action. So we have some function, f of x, y, z, given here, and these are the three inputs that my company has into its production. So it puts in x, it puts in y, it puts in z. And we have a budget of $24,000. The company can buy x, y, and z for the following prices. What combination of inputs will maximize the production? So we know that g of x, y, z minus c equals 80x plus 12y plus 10z minus $24,000. So this is that right there. And here's my function right here. So in this case, I've got four variables, x, y, z, and lambda. So my Lagrangian function, x, y, z, lambda, equals my function that I'm trying to optimize and then we subtract that from lambda times my constraint function. Okay, so we're gonna get into some fun algebra here. So we're gonna get four equations. The first one is that L partial x, which is the following. So 2/5 times 50 this is my partial with respect to x, and this must be equal to 0. And then partial with respect to y, a little bit similar. and this also must be equal to 0. And then partial with respect to z. And this also must be equal to 0. And then the very last partial derivative. So first of all, what this is saying is that our tangent, for all of these to be equal to 0, our tangent plane in this case, that our optimization function and my budget constraints are tangent to each other. And that creates one of the requirements that will make sure that we're talking about a maximum and minimum point. So then we have the partial with respect to lambda, which is just our budget constraint. Okay, so this is a pretty long and tedious algebra problem from here on out, but it's an algebra problem that you can do. And know also that a lot of computer programs can solve this for you now that you've done this work to set up our system of equations. So I'm just going to hop to the next page where there's a solution, because I don't think it's really worth our time to go through all of this. This is just algebra 2. So if we eliminated z from the first two equations, that let us get x in terms of y. And if we eliminated x from the second and third equations, so here we got x in terms of y, and then looking at the next two equations, we were able to get y and z related. Then we could substitute our x and z values into any of the functions, but the easiest function would be into our budget constraint. So plugging this z value in, we'll get that in terms of y, and plugging this x value in gets everything in terms of y. So we're able to find out that y equals 500, and then we can go back to our equations to get that x equals 150, and into here that z equals 600, which lets us know that this is how much we should be selling. Or that's our maximum production. So this is a big topic, the idea of Lagrange multipliers. But just to summarize it, if we have some function that we're trying to optimize and some constraint function g, basically just the gist of the Lagrange multiplier is that a max or a min will potentially occur on the boundary of the constraint, such that my function that I'm trying to optimize will be tangent to my constraint function. So where this is true, there could be a max. There will be a max or min. So this Lagrange multiplier lets us look on the exterior. For our interior, we already had a method. For our interior, we just looked at when does our gradient function equal 0. Because when it equals 0, we know that that is a local max or min. All right, that's it. That's a lot, but that's it.